So again, welcome to our webinar, Improve Sustainability and Performance in Industrial Applications with U.S. Soybean Meal. I'm your moderator, Chris Weigel from OmniTech International. We really appreciate you spending your lunchtime with us today. With us today, we have three industry experts, each with a unique technology utilizing soybean meal in commercial industrial applications. First of all, we have Mike Berkland from Solenis. We have John Dietl and Larry Sacchefaro from APS Grupa, and Alan Snipe from Crossplane Solutions. Now, before we dive into our presentations today, I'd like to show you an overview of soybean meal derivatives, specifically from white flake processing. And these are used for industrial applications. Michael Berkland is going to dive into this a little bit more during his presentation. However, I'd like to point out to you the abundant volumes of meal derivatives right here in the United States, starting off with 45 metric tons of meal and also substantial availability of soy flour, soy protein isolate, concentrate, molasses, and even hulls. Now, the USB is motivated to work with industry to develop and commercialize soybean meal applications. Just last month, USB announced the winners for their Soy Innovation Challenge. These award winners received from $10,000 up to $100,000 in their award. And then furthermore, in collaboration with the Yield Lab Institute, they are sponsoring yet another Soy Innovation Challenge. If you'd like to learn more, please take a picture of this QR code on the slide or reach out to us after this webinar.
Okay, thank you very much. I appreciate it. Thank all of you not only for being here today, but for allowing APS to be part of this conversation. I hope what we have to share today will be of some value to you. And maybe even if you're working on a current project, it'll help you find a way around some of the things you're trying to work on or spark innovation for a new project. Before I get started, you'll notice that we do have a deck of slides. Chris is kindly going to switch those slides for us when I ask her to. I won't be going slide by slide, word by word. The battle scars I've built up over the last 36 years in this industry made it easier for me to just try to explain this as I'd be meeting somebody in the airport and telling them what I do for a living. So if you see a line or bullet point or something and it doesn't make sense to you, raise it up in raise your hand, or you put it in the chat and we can discuss it at the end if you want, or if it's real brief during the conversation. So with that being said, I want to introduce you to our company. APS Grupa is located in Chicago, Illinois. And we basically have two sides of the business. We have the food side and the industrial soy protein side. If you go back one, thank you. The food side is more contract tolling, specialty blending. One of the reasons I listed it here is that over the last 25 years they've been doing this. They've become very dynamic in logistics and helping us get our products to our customers the way they need to. It's not something I've been privy to in the past, and it's very, very nice to see that innovation happen in that area. But what we will be talking about today is APS Grupa, who manufactures the soy polymer under the ProSoy brand name. Now, some of you might remember a product called ProCoat. It was made by Protein Technologies International, and it was produced by them. Then DuPont bought them out over the years, and that was the gold standard. That product, everybody in the industry, and I'm basically going to be talking about paper coatings and ink manufacturing, knew what was going to happen when they put that product into their formulation. Over time, though, with regulatory restrictions and some things that were coming up in the industry start forcing us to make some changes so we can meet the regulatory requirements. And rather than putting the time and effort and a tremendous amount of money it took into the current plant to fix those issues, the decision was made to reformulate to get some of the functionality we needed and produce it on the food side. And the product that was made then was called Soybean, okay? And it worked. It helped people get to where they wanted to go, but it was a little bit different with respect to handling and some of the different things that people were used to doing. And so that gave APS an opportunity to say, hey, go ahead, Chris, next slide, please. They said, you know, we've got a lot of researchers and manufacturing talent that came to us from the DuPont organization, and we're just starting out in this industry. Our vision is to be able to make a product that would perform like the old Procoat product, but meet the regulatory requirements. And they went about doing that. Next slide, please. So they built and when I say state-of-the-art plant, I don't mean that as just a marketing tagline. It is really and truly a state-of-the-art plant that produces absolutely consistently with a lot of first-pass quality. But what's unique about this system is in the event something would rise, like the regulatory compliance concerns are an industry trend. Right now, we're talking about people that want to get away from petroleum-based products and go to more plant-based products. We can make those developments almost in parallel to our standard manufacturing process. And I find that absolutely amazing. Go ahead, Chris. So how do we do that? Earlier on, you saw a flow chart. Basically, when you take the bean from a field, it's got to undergo several iterations. It's crushed, it's defatted, it's moved all around before it finally gets to us as a defatted flake. And that's where we start our process. Okay, it has about 40% protein and some things in there that we want and we don't want. And we go through a series of chemical, mechanical, and thermal manipulations on that product to get the molecule we want, to get the functionality that our customers are looking for. Okay, go ahead, Chris. So what I really want to drive home on this slide is that whenever I talk to a potential customer, somebody who's trying to work on a project, I speak in terms of what the molecule does. Okay, this is a molecule that is extremely strong binder. It is stronger than SBR latex in many cases, but it is plant-based and is renewable resource, okay? But what's unique about this product is it's both amphoteric and amphophilic. So you have pluses and minuses that are running around this with typically a higher net negative charge. And you also have water-loving and water-hating portions of this molecule. In addition, it's a non-thermal plastic, so heat resistance is absolutely off the charts good. And it is an excellent film former, okay? So what does all that mean? Chris, go ahead. Next slide, please. Well, when your product arrives to you in mill or wherever your R&D group, it'll be a dry powder, typically an off-white color. And these are the bulk densities, solution solids that you can go to like 20% plus as far as solids go. The one thing I want to point out here is that you're looking at the slurry pH that says 8.0 to 9.5. And we have that in there not to confuse you, but to really drive home the fact that the product arrives at 4.4 to 4.5. If you take that product and you put it in the water and start mixing it, it's going to look like a bunch of sand being mixed up in the water. It's not until you add an alkali, and this is the way our customers have to use it. They have to be able to get the pH up to between 8.0 and 9.5, where this molecule goes from something that would be like this size and hydrates to something that would be like a baseball or a softball. Now, it doesn't really get that big, but it's just comparison. And why that's growing is because you are actually starting to get dynamic water holding. Okay, Chris. Next slide, thank you. So in paper coatings and recycled paperboard, unbleached kraft, what it means in these type of coatings, these are some of the people that use it. When you get this dynamic water holding, you got to think about this molecule as a colloidal suspension, not a solution polymer. Starch, latex, polyvinyl alcohol, those all thicken in the water phase. They do a great job at what they're supposed to do, but you're thickening in the water phase, okay? Whenever you go under a pressure pulse, and if you're metering off a paper coating, or you're going under, if you're on a printing press and you're going under some shear, that water will tend to evacuate and cause scratching, surface imperfections. It's a multitude of other things that can happen. With this colloidal suspension, you'll go under a pressure pulse and then level on the other side, okay? That is very, very desirable from a paper maker standpoint. In addition, you have a non-thermal plastic adhesive where you're taking out some of the latex, you're putting in some of the poly or the Prosoy, and what's that doing is that when you dry that coating at the end of a paper machine and you roll it up in this great big roll, you have to unroll it to break it down to a web that will allow it to be printed on a really fast offset press, okay? And what that does is it keeps the lint from coming off the backside of that paper and getting on the surface. You can't see the lint when it does that, right? It doesn't show up until you start getting really low impressions between wash-ups on a paper or on a printing press, and they file a claim, it costs you a lot of money. You want to go to the next slide, please? So if you think about it, this is really a dynamic molecule. It gives you dynamic water holding. It gives you thickening, a lot of extra strength. And the amphoteric part is the part I want to talk about now. If you're in a kaolin coating, you have these kaolin plates that flip around in a coating. Typically, you also have some TiO2 that will be used to improve opacity, because kaolin, when it gets wet, has a very poor refractive index, okay? What the Prosoy does is it allows these plates to go face to edge in a lot of its formation in there, okay? And that gives you a much more structured, more porous, more uniform and porous surface. It allows ink to come in at a measured pace. It allows glue to come in at a measured pace. With the excellent film forming that we provide, it allows all that to stay stable and keeps more coating on top of the board. So again, in a comparison's sake, a synthetic formulation will give you a coating that's about that thick at 1 pound, and one with our product into it, we give you one that's a little thicker, okay? So when we talk about these benefits, you say, okay, what does the customer get out of it? What's their benefit? Well, there's a couple different ways that you could go about getting this benefit. You could cut coat weight, which would save you a bunch of money, a whole lot of money, depending on how much board you're producing. That's very hard to control. We typically say that, the TiO2, because it is distributed more uniformly throughout the coating matrix, you can start pulling a little of that off. You can start pulling out, go with a lower total binder level. Those things are a lot more easy to control than it would be to start cutting coat weight, although it is possible and it has been done. But I guess really it just gives a much wider operating latitude to any paper maker or anybody that's wanting to use it in their formulation. They don't get the phone calls at midnight because they're having trouble getting appearance, or they're having trouble getting their brightness. The same type of principle applies to inks. If you put us into an ink formulation, you can take out a product that is made from petroleum base, put in a more sustainable, a more environmentally friendly product that will give you the thickening and will also keep you from getting blisters when you go through the drying process on a real fast offset web press. And we go smoking through there and start drying the printing ink real fast, and all of a sudden it starts popping. That's typically what'll happen with something that releases water too fast. In addition to that, after you cut the board and it stacks on top of one another, it prevents scuffing of that ink on the board. And that's why a lot of our customers will use it in that type of environment. So that's pretty much what it is that our product does. I know it's pretty much a 30,000-foot view, and I'll be glad to answer any questions I can. I'm not a scientist, can't go too deep in the weeds, and unfortunately, what we do is very proprietary, and I don't want to take a chance on making one of our customers real mad. So I will answer any questions I can. So please go ahead.
Don, that was a great presentation. I learned a lot today, and I thought I knew a lot about your products. I mean, especially these are applications we have not thought about soybean meal in, the paper coatings, paper board, the flexographic inks. So thank you for that. I think we have a number of questions, and Brett, I see that you also had raised your hand. So if you wouldn't mind putting your question in the Q&A box, that would be great. Ram has the first question. Can you elaborate on the regulatory hurdles you mentioned in the introduction?
One of the regulatory hurdles was REACH compliance over in Europe. Very, very strict. It was something we could have gotten around, but it would require a ton of reporting. It'd be more costly to do that. And that was one of the things that led DuPont into changing the formulation.
And again, Brett, I saw you raised your hand, so I don't know if you had a question, but if you could put in the Q&A box, that would be great. And then we could answer your question. Larry, is there anything that you wanted to add?
Actually, I think John did a great job covering just about everything. So if there are any questions, I'd be also willing to answer them.
Yeah, Larry can get a lot deeper in the weeds chemically. He was a scientist I've worked with for years and years that actually helped develop a lot of this technology.
Wonderful. So if you're interested in learning more, you have their contact information right here. We ask that you contact them or take a screenshot, and we can also get you together with them. Okay, and at this time, I'd like to turn it over to Michael Berkelin from Solenis.
Thank you so much, Chris. Thanks everybody for coming to participate today. My name is Mike Berkland. I work with Solenis, and today I'm going to talk about our soy-based adhesives, a history of protein adhesives, and the current status of the technology. Next slide, please. So I'll start with a general overview of protein adhesives, kind of a historical overview, talk a little bit about soy adhesive history, get into some of the aspects of soy flour as a protein source, and finish up with going through our Soyad adhesive system, and then talk at the very end about some things that I think are really where the industry needs to go in terms of improving soy adhesives. Next slide, please. So protein adhesives have been used throughout history for as long as we can track, dating as far back as 6000 BC. Neanderthals used animal protein to waterproof cave drawings. The Egyptians had some written formulations for protein adhesives as early as 2000 BC. A variety of protein sources have been used for adhesives over the years. Collagen proteins obtained by boiling animal parts, proteins from dried animal blood, casein protein from milk, proteins from boiled fish skins, and I think most recently proteins from vegetable sources such as soy, wheat, canola, etc. All of these proteins have been useful in various markets, but many of them have been replaced either completely or mostly by some kind of a synthetic polymer. Next slide. So what makes proteins interesting as adhesives? Proteins are polyamides composed of a unique sequence of amino acids. The amino acids can be separated into polar and non-polar, as well as acidic and basic. And really, they offer a variety of side chains that have chemical moieties available for reaction. It's important to understand that proteins have several layers of structure, and in nature, they really have one structure that correlates to a particular biological function. So the structure of proteins, primary structure is really that unique amino acid sequence that defines a protein. There is a secondary structure, which can either be short range or long range, but ultimately really comes down to, the formation of alpha helices and beta sheets to get that three-dimensional conformational structure. Important to getting that correct tertiary structure is the idea that you'll have some kind of a hydrophobic collapse, wherein all of the hydrophobic material will bury itself on the interior of a protein. Obviously, many of these are in aqueous solutions, designed for aqueous solutions. And so you get this very unique tertiary structure that's stabilized by a variety of physical hydrogen bonds and van der Waals forces, but also there can be some covalent bonds in the forms of thiol bridges and other, post modification, if you will. And finally, you have this quaternary structure, which would be, excuse me, the association of different proteins to form a macro complex. And again, those become very important in nature. So, the combination of all these different amino acid side chains and all of the different structural options really make proteins a very good choice for adhesives. One of the things I think we lack right now is a good understanding of what kinds of structures in proteins make good adhesives. And that's an area I think is wide open for research. And generally speaking, this is not always the case, but protein adhesives tend to lack the wet strength that's required for most modern standards. And in order to get there, you do have to have some kind of a cross-linker present. Next slide. So in the 20th century, soy really became the protein of most interest in industrial applications. That continues today. The first patent for a soy-based adhesive was issued in 1923 to Otis Johnson. Those types of adhesive formulations tended to be very high caustic, low solids. They had excellent dry strength. They did not have much wet strength at all. There were some tricks that people tried to use, and I'll talk about those in the next slide. But it was really part of the larger chemergy movement pioneered by George Washington Carver in the 30s and 40s. This idea that we need to bring the farmers closer to industry so that we can make industrial products from agricultural materials. The picture on the lower right is a picture of Henry Ford, sort of showing off the strength of his bio-based materials that he used in his car. I think that's a bumper composed of hemp and a variety of other materials. Soy adhesives themselves were widely used in plywood for the first half of the 20th century. Most of your interior plywood was made with soy-based adhesives. And ultimately, they were replaced by the synthetic formaldehyde-based adhesives, phenol formaldehyde, urea formaldehyde, and melamine formaldehyde. And again, that's really traced back to, I wouldn't say issues, but problems or issues with performance under wet conditions. The synthetic formaldehyde-based adhesives tend to outperform soy-based adhesives in that regard. Next slide. Over the years, there have been a lot of strategies used to improve the wet strength in soy-based adhesives. The older formulations used a variety of additives. Blood proteins would be added for their coagulation or hydrophobic character. Silicates and salts have been added to improve ionic interactions. Sulfides and a variety of other chemistries been used to try to modify side chains and get more reactivity. And then again, direct cross-linking with something like a dialdehyde also has been employed in the past. There was a lot of work done blending soy with phenol formaldehyde resins. My opinion of that is generally that soy behaves like a filler. You certainly will get some dry strength out of it, some structure to the adhesive, but it doesn't really incorporate directly into the resin matrix. Epoxides and kochia type resins, just sort of pre-PAE like resins, but effectively smaller molecular weight, but things that can directly react with side chains on the soy are also viable. And then most recently and certainly important to Solenis is the use of PAE resins. Next slide. So if you take a look at soy on its own, again, you can formulate it to be a pretty good dry adhesive, but once it gets wet, it falls apart pretty quickly. Here we see some lap shear data. Taking just the soy, you've got a decent amount of dry strength. As soon as you soak it or boil it, you lose pretty much all of your strength. And the addition of a PAE, this particular one is a CA1000 PAE resin, it greatly improves both the dry and the wet strength of the soy flour, and really gives you an opportunity to be able to bond and hold that bond in a wet type of a test. Next slide. So the soy adhesive technology really is based on that idea. Soy flour plus PAE resin will give you an adhesive that is really pretty good at bonding wood and lignocellulosic materials. We typically target only interior applications. The reason for that mostly is because certainly in North America, wet wood failure is a real piece of the equation in terms of getting to pass that. And soy flour remains fairly hygroscopic. It absorbs water, it softens, and it's tough to get that material to be as strong as the wet wood. So most of our work is focused on interior applications. Next slide. So we use soy flour as our protein binder. I'll talk a little bit about where that comes from. So soybeans, as they come out, contain both oil and what we'll call meal. It's about 20% oil, 80% meal. The oil has the greater value of that mass, but the soybean meal can be processed to make a variety of different products: soy flour concentrate, soy flour itself, and soy flour isolate, really with increasing amounts of protein content in each of them. Next slide. So this is a very busy slide. I apologize for that, but I like to look at this and remind myself that lots of stuff happens to soy before it shows up to be used in an industrial process. So you start with the whole beans, the hulls are removed, the beans are then crushed and the oil is extracted with hexane. And what's left is what's called these defatted white flakes. So depending on how you process those flakes, you can get a variety of different products. If you do more of a traditional oven type drying, you'll end off on the left side of the slide heading down towards soy flour that is a lower PDI. PDI, for those who don't know, is protein dispersibility index. It refers generally to solubility, though it's not exactly what it is. But the idea is that you have some amount of thermal processing and treatment, and the more thermal processing you have, the more denatured or non-native like your proteins are in the soy flour. If on the other hand you go towards the right and do more of a flash desolventization process, you can end up with higher PDI soy flour that you're really looking at native structures inside of the for those proteins in the flour, and that material can also be further processed to produce enhanced protein products, we'll call them. So the first step would be something like an isoelectric precipitation to remove the soluble carbohydrates. That would give you a soy concentrate. That material could then be put back into solution, remove the insoluble carbohydrates to give you a soy isolate. And then generally speaking, both of those two types of products are then further treated either by jet cooking or enzymes or some other method. And really that's done to give you specific properties, typically in food. And so there are a variety of products out there available for using soy material in an adhesive system. Next slide, please. So soy flour itself, generally this is the breakdown: about 50% protein. These are all plus or minus 5 or 10% depending on particular processing. There's about 28%, 28 to 30% carbohydrates. Those are pretty evenly split between soluble and non-soluble. Soy flour will always carry some amount of water with it, typically around 5 to 8%. There's some ash left over from salts and things like that. The 2% fat's probably not accurate. I think they're pretty efficient about getting all that oil and fat out of there. So that may not be relevant. But then this idea of neutral detergent fiber, I think of that really typically what happens is the hulls are ground up and put back into the flour to really modulate that protein content to just what you want. So it really comes down, I think they're more like insoluble carbohydrates and things like that. It's important to realize that soy flour is very much a particulate. When you take soy flour and put it into water, it does not form a solution. There are certainly soluble components of that, but you really do have this particulate suspension in water. And so I think it's one of the things that we've changed our thought process on is we no longer think of this as a bunch of proteins like spaghetti waiting to be cross-linked. It's really more like sticky rice. You've got these little particulates. They have some amount of functionality that is soluble and available, but much of it is not, and it is stuck in this little particulate material. So it's important, I think, to think about that when you're trying to formulate or do chemistry with soy flour. Next slide, please. PAE, on the other hand, is a thermosetting water-soluble polymer. It's been used as a wet strength additive in paper products for more than 50 years. We tend to go with reasonably low ratios, about 10%, but can go all the way up to 40% in terms of the PAE soy ratio. And that really, we use that to tune to any particular kind of process or performance deliverables that are necessary in terms of the products we're going after. Next slide. Pretty simple molecule. It's really a condensation reaction between a diacid and a diamine. If we use adipic acid and DITA, diethylene triamine. If, for example, you replace DITA with hexamethylene diamine, that would be the nylon 6,6 polymer that is quite ubiquitous. So once the prepolymer is made, it's treated with epichlorohydrin, and ultimately what you're after is that little blue chemical moiety there, called it a zetadinium ion. It is a very good balance of reactivity and stability, and a quite reactive molecule as well. Next slide. So if you're looking and thinking about azitidine, it will really react with any nucleophile. So alcohols, amines, phenols, carboxylates, thiols, there is reactive ability there. Certainly, each one of those has its own particular kinetics. But if you recall back to the amino acid structure slide, proteins and the amino acids contain all of these nucleophilic chemistries, and that's, I think, why we believe that the PAE molecule and soy are a really good match in terms of making a cross-link adhesive system. Next slide. And this really is kind of the take-home slide for us. You blend your PAE resin with soy protein, you apply that to a lignocellulosic substrate, and when you cure and age that material, you get all kinds of bond formation. The soy itself will form physical bonds to the wood substrate. It will also form physical bonds to the PAE, and the PAE will form really covalent bonds with the wood, as well as covalent bonds with the soy proteins, to form this, ultimately cross-linked water-resistant PAE soy complex. And that's really the basis of the Soyad technology. As I mentioned, there are a number of other soy protein products that can be used. The soy concentrates have their soluble carbohydrates removed, so they're a little higher in protein content. The isolates have both types of carbohydrates removed, soluble and insoluble. So you really have, pretty much a protein system. They're used for a variety of specific properties in food applications. They do have some they are somewhat problematic for use in adhesives. The biggest problem really is the low solids, high viscosity issue. Part of manufacturing wood products is the removal of water, a hot press. And when you have so much water to remove, it's really hard to overcome, get the strength you need while removing the water that you have to get rid of so that your panels don't warp afterwards. So as high as solids as possible is ideal. And that's something that these kinds of products definitely struggle with. I think maybe even more so than that would be price. The processing these materials definitely increase the cost of them. And I'll also say availability. I think that these materials are made in large quantities, but in terms of using them globally as an adhesive, there just really isn't enough of that material out there, and the soy flour offers a much better price and properties kind of balance to those things. Next slide. So this will be my last slide. I just want to talk about this a little bit because I think this speaks to the future of where soy, advancements can be made in using soy as an adhesive. So this little chart was a really nice piece of work put together by Chris Hunt and Chuck Freihart at the Forest Products Laboratory. And really the basis of the experiment was, well, how much interference is the carbohydrate doing to the adhesion? And so we start on the lower right-hand part with the soy flour, and effectively went through a lab process to create lab protein isolate, removing those carbohydrates. And then just checking the adhesion of those two products, 50% protein versus 95% protein. There is a moderate increase in wet strength, but it is nowhere near what's necessary to make, a viable wood adhesive. If you take that high protein material, the lab protein SBI, and you then jet cook it, you get a dramatic increase in your bond strength. You also get a dramatic decrease or increase in the viscosity of that material. But at that level where that wet strength is showing, that is very much at a place where that material can be used as an adhesive effectively in these wood products. Most of the commercially available, if not all, isolate is jet cooked, and so in this experiment they also obtained a jet cooked isolate material, added the carbohydrates back, which again you can see did decrease the wet strength by an approximately the same amount that was increased by removing it in the regular flour material. So the carbohydrate really is, I think there's a lot of questions for a while, is the carbohydrate just a filler? Is it doing anything? And I think the answer is no, based on this material. But interestingly, if you take that commercially jet cooked material isolate and you then put it in a wet autoclave, you can actually lose a substantial amount of the adhesive capability. And so I think, from here, it kind of made us change our ideas about what was really going on in a protein-based adhesive. The carbohydrates are not really a major determinant of the performance. They're not participating, but that protein structure really is important. And I think we've kind of started calling this coalescent gelation. The idea that you want to get your proteins close enough together that they can interact, but you have to give them some time to be able to entangle, intertwine, form this kind of gel material. In doing that, obviously, you're building a significant amount of molecular weight and with that viscosity. So the idea, I think, moving forward for us is there some kind of a Goldilocks treatment or balancing of, getting this gelled or pre-gelled material to a state that gives it the best possible outcome for adhesive performance, but without, some of the drawbacks in terms of, like a jet cooked isolate, for example. I think from our point of view, I think there is a lot of room to get there, and I think that's really where the research, I think, has a lot of potential. There is a significant amount of research and literature out there about modifying soy proteins to give you a specific effect in food, and very little out there in terms of modifying soy proteins and trying to define structures that give you a great adhesive. And I think that's a real lacking in terms of literature than what's out there. So that is my story. I very much appreciate your attention, and I would be happy to entertain any questions you might have.
Michael, that was an excellent presentation. You are just a wealth of information, and congratulations to yourself and your whole team at Solenis. I mean, you've been commercial in the Soyad for probably close to 20 years and engineered hardwood plywood. Is that correct?
Yep, the earliest work was done around 2005 in terms of commercialization. So yeah, it's been almost 20 years that we've been working on this and making improvements as we go along.
So in addition to hardwood plywood, can you speak to some of the other key applications that you've been successful in commercializing?
Yeah, I mean, I think, we did a lot of good work in particle board and MDF, particle board especially. We have products that can fill that from a manufacturing, a performance requirement and a processing requirements. The issue really comes down to cost. Urea formaldehyde is cheap, it's strong, and it's fast, and it's a tough beast to tackle. I think some of the regulatory push for removal of formaldehyde helped us along. But I think also outside of that, the cost really was an issue. And, when we started this, PMDI isocyanates were not as ubiquitous as they are now. They were, in fact, at some point they were on allocation for a few years, and that capacity ramped up. And I think really that molecule took over, UF in terms of a no added formaldehyde system. It has its advantages and disadvantages, but from our point of view, we just didn't. The formaldehyde regulation wasn't enough to drive people to the cost. Now we are seeing differences now in the market space in terms of people wanting bio-based materials, not just no added formaldehyde. So again, I think there is room to move. We do have active operations, active research going on in terms of particle board and some of the bigger composites types markets. But currently, most of our business is in hardwood plywood and engineered wood flooring.
Mm-hmm. Well, that's great. That's a big application in itself. So we have a question from Ram too. He was asking that, are there any residual EPI content in the final product?
Yeah, no. So early on, yes, but it depends on. I mean, obviously, we can manufacture PAE to be very, very low in that type of material, and so when you're talking about 90% is water and soy and 10% is PAE, a generation 2 PAE is effectively invisible in terms of epi residuals from the PAE. Yeah, very good question.
Okay. Are there any more questions from the audience? Well, thank you, Michael. Again, you're a wealth of information. We really appreciate this. So thank you for your participation. And we are going to jump to our next presentation. And that is with Alan Snipes. He's managing partner at Cross Plains Solutions. So Cross Plains has developed a unique, very high performing spider fighting foam. And you're really going to be thoroughly impressed when you see some of the video demonstrations that he'll be showing us. So at this time, I'm going to be turning it over to Alan.
Thank you, Chris. And I want to thank John and Mike for explaining the virtues of the soybean meal and flour that is available to us to use. Last year, we were approached by the U.S. Soybean Board to help develop a training foam for a leading firefighting group that was in need of something to be able to train with that contained no PFAS components. And we were able to put together a foam that we tested in November of last year at a leading firefighting training station in Georgia. If you'll advance, Chris, will. A little bit about us. We have been working with soy-based solutions for the carpeting industry and the bedding industry for about 12 years. Recently have ventured into the firefighting foams. Our basis of scientists that we have working on this have a combined group of 100+ years of training and experience in agricultural based products, particularly in the proteins. And we're using this to help engineer the PFAs out of firefighting foams and to develop a home for meal and flour, and at the same time trying to help protect the 1,117,000 roughly firefighters across the United States that deal with these products on a daily basis. Our product is able to be used as a wetting agent at a 0.1% solution up to a firefighting solution of 3% that is capable of putting out fuel fires. And we're getting into the phase now to where we're starting to offer this on a commercial development. Next, Chris. Again, using the soy products, we're able to create a concentrate that is roughly 100% natural. It's over 70% bio-based and contains over 50% of its components are soy meal and flour. It's ready biodegradable. We are currently under testing for soil testing for biodegradability that our goal is to be 60% biodegradable in 180 days. We surpassed the 60% at 47 days, and we're approaching 100% in less than 90 days. So it's a very good biodegradable product that is very effective so far. Next. The soy meal that we're using and flour, it's readily available. It's back integrated from the agricultural supply chains. We use the proteins in there to help enhance the foaming capabilities of the product and create the wetting agents that we need. Next. Our intent is to have our soy foam product to be able to be used in wildfires as well as domestic fires. We're currently working with the U.S. Forestry Service in getting our product certified to be able to be used on wildfires across the U.S. Next, Chris. Again, these are the formulations that we're striving for. One thing protein-based fire foams have been used in the past, and part of their fallback was that they didn't have much of a shelf life. We have trademarked and patented our process that gives us an extended shelf life. We use no fluorinated chemicals at all, including the banned PFAS. We have no flash point, and we're reworkable after being frozen. We are, again, Ready Ultimate, biodegraded, and septic systems and whatnot. We're deemed non-toxic through 2021 and 201 for invertebrates and algae. We're slightly toxic to bullhead minnows, which is a very, very hard certification to meet. And we're certified by Beta Analytics as being 70% bio-based. This is a video that shows at our training facility where, first of all, we wanted to make sure that we could create a foam, which we did, as you see in this video. The next video is, I think we got duplicates on these, Chris. This simulates a brush fire. It's actually pallets that are piled up and allowed to burn and get to a point of where there's an excessive amount of heat. They'll adjust the hose to begin with to create the flow of the foam. This, I think, is at a 1/10 of 1% solution. And it will, you'll see, it pretty well puts the fire out pretty quickly. One other point, part of the basis of the product that we have to have not only is the ability to put the fire out, but to control the fire after you've put it out. Once this stack of pallets was put out, about an hour later, we went back and attempted to relight them with a torch, and the wetting agent was such that we could not reignite the pallets. The next simulation that we show is simulates a house fire. This again is at the training facility in Georgia. You can see the fire within the structure. The firemen go in. Again, I think this is a 1% solution that we attack the fire. They go in, they locate the fire, and they put it out. And I think from the time that they started spraying the foam on this until you see the firemen come through the doorway there is about 18 seconds. And they said that they noticed a marked reduction of temperatures in there once they started spraying the foam on the fire. So that's important in our training. This again, after it had been extinguished, we waited about an hour and tried to reignite it, and we could not reignite it. We want to thank the Soybean Board for their monetary support and technical support. They've been integral in helping us find testing labs and find raw materials, and they have just been a wealth of information, and we appreciate all of the help that they've given. Chris, I know that was a little short, but we'll be willing to take questions now.
Yeah. Love those videos. I mean, that's really telling. Well, I have a question until we have the audience maybe populate a few more. What's your plan for full-scale commercialization? Do you have an anticipated timeline?
We, yeah, as soon as possible. The stumbling blocks that we have on commercialization right now are that each of the the segments that we go to and try to push this product toward commercialization is that each entity has its own set of regulations and testing requirements and whatnot that have to be done. And these tests don't happen overnight. I think the soil biodegradability testing, for instance, is a 6-month test. You have to have extended shelf life testing, but there's nothing out there that we found so far that we feel like we can't pass. Our corrosion tests that we've done internally, while we're just now getting to a point of being able to address those in lab settings. Everything is very positive there. That we know that based on our formulation, there should be nothing there that creates a toxic issue or a safety issue. And we're able to put the fires out, which is the important thing. We've had discussions just this past week with the U.S. Forestry Service and initiating testing for their requirements, as well as the Department of Defense. That is, we had talks as late as yesterday, and they're going to help us with a lot of the testing that we need to do at the U.S. Naval Testing Facility and on the Chesapeake Bay.
Definitely a lot of motivation for people to transition over to your product. I mean, compared to look at the chemistry that is used today, very much motivation there. Chris Hunt has a question. Is the basic functionality of the fighting foam to create and maintain a stable foam?
We can create a foam, and we do create a foam. Obviously, the higher concentration of the usage creates a thicker bed of foam. On residential type fires, you're looking more for a wetting agent than you are a foam per se. So you want to be able to go in and put the fire out and wet the fuel source to a point that you're cooling it down to eliminate the fuel for the fire. What we're in testing for now is to make sure that we have some residual applications for when we spray the foam, say on a wildfire or something, that if you want to spray for a fire break, once you spray the foam and the water evaporates, we want to make sure that we've got an effective film there so that the fire would not be able to cross it even with the absence of water. So not necessarily having the foam itself there, but having the residual firefighting properties of the gel or the foam itself.
Excellent. Well, we'll be cheering you on. We look forward to this being the commercial marketplace. Too bad it wasn't available to help out the poor people in Canada with their recent events. So thank you, Alan. Great presentation. And that concludes our presentations for today. I want to thank Michael, John, Alan for all participating today. You seriously are a wealth of knowledge, and we hope the rest of you enjoyed the webinar and are inspired to develop, commercialize, or use soy meal in your future product offerings. So on the behalf of the United Soybean Board, Omnitech International, and Smith Buckland, we thank you for joining us today. Please visit our website, New Soy Uses, or contact us directly if you have any questions or like to learn more about USB funding. Thank you.
Thank you. Take care.